We've talked about just a few kinds of forces and about how to put them into a free body diagram. What we haven't done yet is discuss what to do when we have our free body diagram. This video is about translational equilibrium. First, translation. In math terms, translation just means straight line motion, sliding. We're not rolling, we're not rotating, we're just moving. Equilibrium means we've achieved some kind of balance. Translational equilibrium specifically means there are no net forces acting on our object, and we can use this to solve for an unknown force. Maybe I have a crate with a mass of 50 kilograms, conveniently labeled in big letters right on the crate, and it's sitting on a scale. That's my scale. Sitting on top of the crate, there's a box with a mass of 40 kilograms. Also nicely labeled, but that box is being lowered on right now by a rope, and it's in the process of being lowered into place. So the rope that's lowering it carries a tension of 150 newtons. And I would like to know, what is the readout on the scale? First things first, we should talk about the scale. A scale exerts a normal force upward on whatever sits on top of it. The scale is able to read the magnitude of that normal force. We can talk more about how it does that in a later section, but that's the number that it displays. So the scale readout is the normal force that it exerts on the crate. Here we go. I'm going to start with a free body diagram, and I will draw one for this bottom box. So on that box I have this downward force from gravity. I will call this thing box 1, this thing box 2. So I have this downward force from gravity of m1 times g. I have an upward force from the scale, and I have a downward force from block 2. F on 1 from 2. That's all I've got. I'm going to call upward my positive y-axis, and I have a free body diagram. I will also draw one for the bottom block, or for the top block rather, I'm sorry. So on this guy, I have a tension force that points upward, and it is 150 newtons. I have a downward force because this block has mass, m2g, and I have an upward force from the block underneath it. So this is F21. I'm going to call upward my positive y direction, and there is my free body diagram for block number 2. Now one thing, I know that this is in static equilibrium, in translational equilibrium. So if this is in translational equilibrium, that means that the sum of forces acting on the box, and on the crate has to be equal to 0. This thing is an uppercase sigma, and it means sum of, or total, summation, however you want to think of that. So I want to look at my 50 kilogram block crate first. What I have an upward force of N, which I don't know what that is. I have a downward force of F12, I don't know what that one is either, but it's downward, so I'm going to call that in the negative direction. And I have an M1G, so minus M1G. Those are all the forces that I have, so that is my sum of forces. that whole thing equals 0. I have n, which is what I'm solving for, but I have another unknown, F12. On to the 40 kilogram block. Maybe I can find another equation there. Total forces. My upward force, I have tension, and I know that one's 150 newtons. I have plus F12. I don't know what F12 is, or F21, they're the same as each other. Minus M2G equals 0. Again, this is my sum of forces. This is an equation I can solve. F21 is my only unknown in here, and I know that these two have to be the same. This one shows up with a plus sign, this one shows up with a minus sign. That's what's taking care of the opposite part of equal and opposite. But that's where we are. So I'm going to take this equation and I'm going to solve it for F21. I'm going to add M2G to this side and to this side. I'm going to subtract T from this side and from this side. And that leaves me with F21 equals M2G minus T. And now I'm going to plug in my numbers. So 40 kilograms, 10 meters per second squared, minus the tension, which is 150 newtons. I like to leave my questions in variables as long as I possibly can, because it's not an uncommon thing to have a part B to a question that says, how would this be different if the tension were 50 newtons instead? And then if you plugged in your numbers right away, then you have to go through and do the whole problem again. This way, I'm down to one equation I can plug in and I'm good to go. 40 times 10, that's 400, minus 150, that's 250 newtons. So I now know this F21, which is the same as F12. This is also, by the way, the contact force between the blocks. Or between the box and the crate, I suppose. Box and crate. So I know that number. I'm going to take that number and plug it in there. My equation says N minus F12 minus M1G equals 0. I now know my F12, so I'm going to stop writing that in red. And I'm solving for N. So I'm going to add F12 to both sides. And I'm going to add M1G to both sides. And I get, on the left side, I'm left with N. On the right side, I get F12 plus M1G. So I get 250 newtons plus 50 kilograms times 10 meters per second squared. 50 times 10 is 500 plus 250 is 750 newtons. That is my normal force. That is what my scale reads out. That's it.